Consider two complex dynamical systems that, to an outside observer, appear structurally identical. Both systems share the exact same node topology. Their edge adjacencies map perfectly to one another. The architecture is indistinguishable. When we run a standard baseline trajectory replay, the outputs align exactly. Both models produce identical responses to normal operating conditions. It is standard practice to look at this matching topology, observe the matching baseline replay, and conclude that the two models are dynamically equivalent. Relying on this baseline similarity creates a severe vulnerability in predictive model transfer. Models that look the same under normal conditions often conceal deep mechanical differences, creating blind spots in our predictive capabilities. To find those differences, we have to test both models beyond their baseline trajectories. We apply a perturbation sweep. This animated chart maps the results of that sweep. We introduce a controlled wave with input noise across the entirety of both systems, designed specifically to test their boundary thresholds under stress. Model A absorbs the noise and successfully executes a smooth regime switch, maintaining stability. Model B hits the exact same threshold and misfires, collapsing into chaotic oscillation. The perfect synchronization we saw during the baseline replay shatters. The trajectories diverge sharply, revealing an error gap that exceeds standard tolerances. The models behaved differently because of hidden causal constraints. Standard baseline replays are mathematically blind to these variables. Without stress testing these recurrence conditions, predictive models lack a defined validity envelope, making their performance outside baseline scenarios speculative. Topological similarity guarantees nothing about behavior under stress. True equivalence requires proving causal consistency when subjected to a perturbation. The Unified Harmonic Systems Framework addresses this specific failure point by strictly defining what unification actually means. UHS rejects blanket claims of identicality. Unification is treated as a disciplined, mathematically constrained mapping process. The methodology does not look for visual or topological similarity. It explicitly audits how well invariant properties are preserved across different representations. By enforcing this rigorous mapping discipline, UHS replaces fragile visual assumptions with mathematically audited boundary limits. You know exactly where the models align and exactly where they break. To validate that equivalence, UHS mandates a constraint-preserving translation pipeline, as defined in section TU IX 04. This flow diagram outlines the 5 ordered stages: descriptor selection, invariant declaration, structural mapping, causal consistency check, and finally, claim strength assignment. The strict sequential order is mandatory. Skipping steps or rearranging the sequence drastically increases the risk of generating a false equivalence. The 4th stage, the causal consistency check, acts as the critical filter. This is where perturbation failures are caught. If a mapping preserves static structure but strips out non-signaling constraints like threshold windows, the consistency filter rejects it. The structural mapping alone is insufficient. Bypassing this specific audit creates significant diagnostic gaps, particularly regarding how a system handles threshold-driven regime switches. Any mapping that removes recurrence conditions during translation is explicitly classified as incomplete. Removing the causal consistency audit from the pipeline directly results in the predictive failures we observed in the initial perturbation sweep. Running this pipeline successfully requires a shared, mathematically transferable language between the source and target systems. This data table displays the TU IX 06 operational descriptor set. These are the specific required variables needed for a valid translation. Specific subsets of these variables are responsible for carrying the unique topological and dynamic properties of the model. Variables like the adjacency matrix map the physical topology, while variables tracking recurrence and threshold context map the precise conditions under which the system switches states. There is a strict requirement for this set. It must remain compact and entirely operational. Keeping the variable set restricted prevents translation audits from becoming computationally unfeasible, while successfully preserving the exact causal memory required for accurate predictions. Model translation is rarely a binary outcome. It is almost never a complete one-to-one success or an absolute failure. Instead, the framework introduces the concept of graded claim strength. This test matrix evaluates mappings across 3 critical dimensions: baseline replays, perturbation sweeps, and boundary constraints. Consider a scenario where a target mapping processes successfully through the replay test and the boundary test. However, under a small perturbation, the mapping misplaces a threshold-driven regime switch. It fails the middle test. The system does not outright reject the mapping because of this single failure. Instead, the mapping is downgraded from an exact Tier 1 class to a bounded Tier 2 class, and the specific residual error limits are mapped mathematically. This Tier 2 mapping retains immense utility. It is still perfectly valid for descriptive alignment and mapping static structures. But because of the downgrade, this specific mapping is strictly barred from being used in predictive transfer claims. Explicit grading allows flawed models to remain highly useful within their declared boundaries, ensuring their errors do not contaminate downstream predictions. The final requirement of the unification process is generating the validated downstream handoff package. This diagram compiles the 4 required components of that package: the descriptor set, the invariant audit status, the claim strength tier, and the explicit failure boundaries. This compiled package represents the audited technical profile of the unification process. Notice that declaring the explicit failure boundaries is treated with the exact same importance as transferring the successful topology. Any translation claim poses an active danger to a system if it fails to explicitly declare the exact mathematical conditions under which the model will break. This data package is built for immediate downstream consumption by the next architectural layer, Module X. Module X relies entirely on this verified package to stabilize compressed aggregate structures and accurately calculate fragmentation risk. The framework dictates a strict rule here. Downstream architectural layers must consume this bundle as a set of hard mathematical constraints. They are never treated as optional guidelines. Downstream system design is explicitly forbidden from rebuilding or guessing translation assumptions ad hoc. The math must flow seamlessly from the audited source. Unification in UHS functions as a rigorous definition of boundaries, establishing exactly where two systems can be treated as equivalent and where their dynamics diverge.